In this class, we will study about salinity. The salinity subject, if you had studied your soil science course well in first year, then this lecture need not be listened to at all, because whatever you have studied there in the soil science course has been repeated here. But it is worth recalling that subject at this place, because the leaching process can be very well understood and that work can be very well done if this concepts involved in salinity are understood very well. You know very well that clay particles are plate-like shaped, and they have a longer linear length and a smaller thickness. And you should also recall that the clay particles are negatively charged. And if soil particles are larger, then they can be treated as neutral. As the size of the clay particle becomes smaller and smaller, more and more charges, negative charges, can be expected in a clay particle. If we want to have electron neutrality in soil, we need to supply cations to the soil particles. Let us assume that we use hydrogen ions to neutralize the clay particles. So you know that one hydrogen ion has one positive charge. So one hydrogen ion can be used to neutralize one negative charge. And you also know that 1 gram of hydrogen ions contains 6 into 10 power 23 ions. 6 into 10 power 23 is, after all, it is Avogadro's number. So it is a number. So 1 gram of hydrogen will have a 6 into approximately 6 into 10 power 23 ions. It's a standard. So instead of hydrogen ions, let us assume that we have 6 into 10 power 23 negative ions. We will take 6 into 10 power 23 negative ions of a clay particle. Instead of hydrogen ions, if we use sodium ions to neutralize it, then we may have to use 23 grams of sodium ions. It is because sodium is 23 times heavier than hydrogen, and one sodium ion will supply one positive charge. So because of that, you need to have 23 grams of sodium. Instead of sodium, let us assume that in order to neutralize same 6 into 10 power 23 negative ions, we use calcium. In that case, we may have to use 20 grams of calcium, because the atomic mass of calcium is 40 times heavier. But each calcium ion supplies 2 positive charges, because its valency is 2. So its equivalent mass becomes 40 divided by 2, 20. So equivalent, previously it was being called as equivalent weight, but it is better to call equivalent mass. So nowadays it is called as equivalent mass. So I would like to recall again, valency means it is the number of electrons an atom uses in bonding. Mostly it is each element will have one valency, but it's not always also true. Sometimes it depends on molecule with which the element uh, forms part of. Depending on that, valency would also vary, that you know very well. And the equivalent weight is atomic mass divided by valency. So these are all the things you know already. And the next concept you know already is the cation exchange capacity. Cation exchange capacity of soil is expressed as mass of hydrogen ions needed to neutralize 100 grams of soil. Let us say to neutralize 100 grams of pure inorganic soil without anything, without any other cations present there, we need 5 milligrams of hydrogen ions, let us assume. In order to neutralize 100 grams of soil, let us assume that 100 milligrams of hydrogen ions are needed. So, in that case, its cation exchange capacity is expressed as 5 milligram of hydrogen ions per 100 gram of soil. And conventionally, instead of writing milligram of hydrogen ions, it is written as milli equivalents. So 5 milli equivalents per 100 gram of soil. So whenever you read 5 milli equivalents per 100 gram of soil, you should expand and understand that MEQ should be replaced with milligrams of hydrogen ions per 100 gram of soil. So instead of using hydrogen ions, if we make use of calcium ions to neutralize it, how much mass of calcium is needed? So 5 into 20. 20 is its equivalent mass, calcium's equivalent mass. So if it is hydrogen, it is 5 milligram, and if it is calcium, then it is 5 times. It is 20 times 5. So 100 milligram per 100 gram of soil. We should keep in mind that whatever you know very well that in a soil will contain different kinds of cations like potassium, calcium, magnesium, ammonium, and things like that. When we express cation exchange capacity, we do not express in terms of each kind of cation. We find out concentration of each Ka, calcium, magnesium, and each of them are converted into equivalent hydrogen ion concentration, mass, and it is expressed. So that should be recalled. Cation exchange capacity is expressed conventionally in terms of hydrogen ion concentration per 100 gram of hydrogen ion concentration needed to neutralize 100 gram of soil. Hydrogen ion is needed to neutralize 100 gram of soil. So we may have K, calcium, magnesium, whatever be the thing. Each one is converted into equivalent hydrogen ion concentration. That should be kept in mind. Next concept is salinity of soil. Salinity of soil is obviously salt concentration in soil water. The criterion used to express the salinity of soil is total dissolved salts. The unit used for expressing total dissolved salts is milligram per liter or parts per million. There is another criterion, it's an indirect criterion that is normally used, conventionally used, that is called as the electrical conductivity. The electrical conductivity depends on the total dissolved salts. So indirectly one can find out electrical conductivity and can relate to total dissolved salts. The unit used for electrical conductivity is deci-Siemens per meter or millimoles per centimeter. Approximately 1 deci-Siemens per meter approximately corresponds to 640 parts per million. Normally for practical interpretation, salinity at field capacity is necessary to be found out. But measurement of salinity at field capacity is very difficult because at field capacity the soil moisture is very difficult to extract water at field capacity from the soil. It is possible, but it is very difficult and it is time consuming and it is costly process. So practically what is done is at saturation it is easy to collect the soil water, and practically and really in the field it is also, the soil is also not saturated because each soil will hold different amounts of water at the saturation. So then it becomes again difficult to have a kind of a standard. So what is done is, whatever be the soil, for every 100 gram of soil, 100 ml of water is added, and all the salts which are in the soil is extracted, and for that soil solution electrical conductivity is found out, and that electrical conductivity is said as EC saturation extract, electrical conductivity for the extract. So that will have a lower salt concentration because we would have added more water. So approximately it has been found that electrical conductivity of any soil at with saturation is twice as that of electrical conductivity at field capacity. So find out electrical conductivity at saturation, convert to electrical conductivity at field capacity, and accordingly make use of that data for interpretation. Next concept is exchangeable sodium percent. We have already seen that cation exchange capacity is a measure of total cations needed to neutralize soil. That is neutralized soil of 100 grams. What is exchangeable sodium percent? It is the fraction of sodium content in total cations. So how do we find out that? Find out the exchangeable sodium content alone in 100 gram of soil and express that into milli-equivalent per 100 gram of soil, and divide that by total, divide that by cation exchange capacity. That is the total number of total cations expressed in milli-equivalents per 100 gram of soil. So after division, convert that into percent by multiplying by 100, then you get exchangeable sodium percent. Actually, finding the exchangeable sodium percentage measurement is very difficult. So scientists found out simplified ways of finding the exchangeable sodium percent, and for that another parameter called sodium adsorption ratio is found out. Sodium adsorption ratio is sodium concentration expressed in milli-equivalents per liter of soil solution. And calcium, magnesium, all ion concentrations are found out from the soil solution in the saturation extract. And they are found with the unit of milli-equivalents per liter, And from the sodium adsorption ratio, there is an empirical formula that is used to find out exchangeable sodium percent. Let us assume clay particles without any cations, clay particles of the soil without any cations. What will happen? All clay particles will have negative charges and they will tend to oppose each other, and there will not be much of cohesion, and there will be more dispersion. It will be like magnets with the same poles. If they are brought together, one magnet will cause a force on the other. In the same way, the clay particles would also behave. Next is a concept called diffuse double layer. Let us see, this is a clay particle. This line indicates a clay particle. On the surface, you will have a negative charges. In the soil solution, if we have salts, and if the salts are dissolved and they would get dissociated, and it will have cations and anions, and the cations alone would get adsorbed to the soil particle, and close to the soil particle a layer, not only one layer, there may be few layers of cations which would be attached to the soil particles sternly, fixedly, they will not move at all, and that layer is called stern cation layer. And after some distance, if you see, there will also be more number of cations and less number of anions, but these cations will move to certain extent, but still their movement will not be as that of in the distant locations. So near the clay particle there is a stern layer and there is a approximate diffuse layer, and these two layers together are called diffuse double layer. And in sodic soils, this diffuse double layer is the culprit, and that causes lots of problems. So if you look at this image, and this image depicts the relationship between distance to clay particle. That means this is a clay particle and distance to clay particle. You take here, 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 like that. At different distances, find out the ionic concentration. Separately find out the cationic concentration and also anionic concentration and plot it. So if you plot, you will get this kind of a graph. So near the clay particle, you will have more of cation, very less, almost nil of anions. As distance increases, both will get increased and both will join together. And after that, you can say that it's a free water. The effect of clay particle on the charges, the effect of clay particles on the cations has got ceased. So until this, you can say that this is a diffuse double layer. Then after that, you can say that this is a free water. Next concept is called hydration. What is hydration? You should be very clear about hydration and hydrolysis. It should not be confused. In case of hydration, what happens is, with the soil particle or cation or anion, with each particle of soil particle or cation or anion, if it is surrounded by water molecules, without water molecule getting dissociated into hydrogen and hydroxyl ions, as a total water molecule, if it gets if a cation or anion or soil particle is surrounded by water molecules, then we call that process is called as hydration. See here, a water molecule should also be it should be recalled that water is bipolar in nature. A water molecule will have on one side it will show positive, it will have a positive charge, and on the other side it will have a negative charge because of the orientation of oxygen molecules and all that you would have studied in physics and chemistry +2. So water is bipolar in nature. On one side it is positive and another side it is negative, and it can rotate. So here it is shown as this is a clay. This is a clay surface, and the legend is darker, filled or cations, non-filled or anions. Okay. So look here. This is an anion. Anion is negatively charged. Anion is negatively charged. And because of hydration, water particles get surrounded, and anion is negatively charged, and the positive side of water particle is surrounded, and if you look here for cation is positively charged, and if you look here, and the water molecules negative side is it gets attached. So here also cation also gets hydrated, and anion also gets hydrated. So water is capable of hydrating both cations and anions. When water hydrates cations and anions, what happens is, and the effect of the cations and anions on the clay particles gets decreased because it is surrounded. So that should be kept in mind. Beyond DDL, beyond diffuse double layer, these hydrated cations and anions can freely move collectively as a group. This can freely move here. But when they are in the diffuse double layer, and they will not be able to move freely in diffuse double layer. So this is a clay particle, then this is a stern layer, and this is the diffuse layer. In these places, these groups, hydrated cations and anions, will not be able to move freely. If they are not able to move freely, then your infiltration process gets affected. So that should be understood with this image. So with reference to each type of cation, like sodium and calcium and all, how this diffuse double layer size behaves, that should be understood. The sodium ions get too much hydrated. They are strongly hydrated. So when they strongly hydrated, lot of water molecules come in between and make the clay particles to move far away. So this causes the expansion. And because of surrounding of sodium by water particles also, the neutralization process because of cations gets reduced, and the negative charge here and this negative charge here will have a more opposing force to each other, and that would also cause expansion. So in case of sodium, there is more possibility of swelling when you apply water. In case of calcium, calcium has two positive charges and they do not get too much hydrated, and the processes in comparison with sodium for calcium is opposite. So there is not much repulsive force between clay particles when you have calcium in between, and the diffuse double layer is also, the thickness is also very less. So in order to have a better soil structure and the soil characteristics, we may need to remove sodic soils with calcium. You have to replace the sodium with the calcium. So that should be understood. And next thing is, you know that pH is a logarithm of 1 by hydrogen ion concentrations. So lower the pH, you will have more positive ions. So if your soil solution has a lower pH, it has been found that you will have more of positive ions at the, this is a clay particle, at the edges you will have more of positive ions in a clay particle. So what happens is, on the surface you have more of negative charges. Here at the edge you have a positive charge at the edges. So this kind of a structure gets formed. So this is on the surface negative, at the edge positive. So it comes and gets fixed like this, and you have a kind of a pack called kind of a structure. They are called floccules. This kind of a formation is good. So in sodic soils and all, if you reduce the pH, you will have a good soil structure. And if you add more organic matter, more gypsum, gypsum is calcium sulfate. So this kind of a floccule formation will be better. So to wrap up, lowering the pH, you will have more of hydrogen ions, you will have a smaller diffuse double layer, and leaching becomes easy. There is not much of swelling, and smaller the diffuse double layer, you will have a more area for easy movement of water. In the diffuse double layer, the movement of water itself becomes difficult because of the forces between the charges. So higher the pH, you will have more hydroxyl ions and larger. It's not, sorry, it's yes, larger diffuse double layer. So leaching becomes difficult. So with regard to when you have more of organic matter, how this diffuse double layer and how cation exchange capacity varies and all, we will see. If you have more organic matter in the soil, you will have more locations for storing of cations. And organic matter content also, the stage of decomposition is important. If you have undecomposed organic matter, then you cannot expect more of cation exchange capacity. If the organic matter is fully decomposed, you can expect higher cation exchange capacity. So higher the cation exchange capacity, then more is the possibility of nutrients that can be fixed onto the organic matter and that can be made use by the plants. So if you have more organic matter, so you can also expect more soil floccules getting formed like that, and the soil structure would be much better. Many times people think that since sodium can be very easily hydrated, in order to leach the soil, one can just apply the water and hydrate the sodium and remove the sodium salts. But it has its own problems, because when sodium is removed, what happens is we are removing positive charges. So it causes the diffused double layer to become larger. When diffuse double layer becomes larger, then again problem comes. The soil structure gets broken down. So even before removal of the sodium, the soil would have got a better structure, and after the problematic sodium is removed, then it will show a lot of structural problems. So it is always better to make use of amendments when leaching of sodic soil is done. That is the reason why the amendment like gypsum, calcium sulfate is used. What is done is, when you are removing sodium from the clay surface, if you place the calcium ions instead of sodium ions, then the thickness of diffuse double layer, then it becomes smaller, and the other problems get removed. Like gypsum, one can also have addition of more of organic matter after leaching of sodium is done, can also be adopted. So already I said reclamation of sodic soil is mostly done by application of gypsum. And now we will see how, for a soil, how can we estimate the gypsum requirement for a sodic soil. The amount of gypsum needed calculation depends on how much of exchangeable sodium that exists in the soil has to be estimated, and how much mass of the soil that we are going to reclaim, that should also be known. Because in a sodic soil, you may have if you take a profile, you may have 60, 90, 20 centimeter like that. Total depth, totally it may have lot of sodium. Removing all the sodium from entire depth is not possible, and also not needed. So normally what is done is, the sodium is removed from the root zone alone, and depending on the availability of money also, normally at least 15 centimeter of soil is treated, and the sodium is removed from that depth of soil. Now we will do a small problem to understand how to do the calculation for estimation of this gypsum requirement. We will take this problem, which has a data like this: 15 centimeter to be reclaimed for 1 hectare of land, and bulk density of the soil is 1.3 gram per centimeter cube, and soil test results shows like this. Calcium is 7.5 milliequivalent per 100 gram, and magnesium is 6.6 milliequivalent per 100 gram, and sodium is 12.3 milliequivalent per 100 gram, and potassium is 1.2 milliequivalent per 100 gram. And all these are all the major cations, and all other cations are negligible. And we plan to bring the exchangeable sodium to 15% of cation exchange capacity. So for that, we need to calculate the gypsum requirement, and we will assume the factor of safety. Take the factor of safety to be 1.25 in order to take into account gypsum purity. We will not have a pure gypsum in the market, and as well as the deficiency of soil chemical reactions and the leaching process. So We will find out gypsum requirement based on chemistry, and we will multiply that by 1.25 to take into account the factor of safety. So gypsum's molecular formula is calcium sulfate CaSO4 to H2O. So it has a molecular mass, molecular weight I call it as molecular mass. So calcium is 40 and sulfur is 32 and oxygen is 16, 4 times oxygen and 2 hydrogens and here it is 2 into 2 and this should be 2 into 1 yes, and 2 oxygens 2 into 16, so it is 164 and valency of calcium is 2 and equivalent mass of gypsum then becomes molecular mass divided by valency, it becomes 82. So this is the equivalent weight or equivalent mass. And the cation exchange capacity is total amount of cations per 100 gram of soil. So each 7.5, 6 points, all these things add. Then you get 27.6 milligram of hydrogen ions per 100 gram of soil. So in that, what is the exchangeable sodium percent? The sodium is 12.3 milliequivalent. So 12.3 divided by 27.6 expressed as percent, then you get 44.6%. So what is the reduction in exchangeable sodium percent needed? And that is what our target is to have 15. Now we have 44.6. So how much reduction needed? 44.6 minus 15. Approximately it is 30%. So in order to bring the 30% exchangeable sodium percentage level, so what is the exchangeable sodium content needed? So if you look at this formula, you need to find out what is the exchangeable sodium content that should be removed. Exchangeable sodium content is equal to exchangeable sodium percent into cation exchange capacity. So exchangeable sodium percent reduction is 30%, so 0.3, 27.6 is its cation exchange capacity. So you get exchangeable sodium content that should be removed is 8.28 milliequivalent of hydrogen per 100 grams. So if you are using calcium, to remove this much charges, so for calcium the equivalent weight is 82. So 8.28 into 82 will give you 678.96 milligram of gypsum. So milligram of gypsum per 100 gram of soil. So this is for 100 gram of soil. So obviously what we need to find out next is what is the weight of soil, what is the mass of soil we are going to treat. So bulk density of soil is 1.3 grams per centimeter cube. So volume of soil in 15 centimeter depth for 1 hectare is 1 hectare converted into meter square, and 15 centimeter into meter, it gives you 1500 meter cube of soil has to be treated. So mass of this 1500 meter cube of soil, so bulk density is 1.3 gram per centimeter cube. It means that 1300 kg per meter cube. So multiply 1.95 into 10 power 6 of kg. This is the mass of the soil. So we have previously calculated 678 milligram per 100 gram. So for this much mass of the soil, how much? So multiply 1.95 10 power 6 into 6896. So conversion factors milligram into kg, and this 100 gram that into again kg, you get 13 to 39 kg or 13.2 tons approximately. So this is a very good calculation. If you know this, then it is very useful for you to write JRF and GATE examinations. So with that we conclude this class. Thank you.